what we are really mean by this is, suppose we have a function which is only lasting for positive t. So, we are taking cos omega c t u t, that means for the negative values of time it is cut off. This we are calling a truncated sinusoid. To find out the Fourier transform for this, we recognize that this is equal to half of e to the power of j omega c t plus e to the power of minus j omega c t times u of t. Now that we have the Fourier transform for u of t, we can find out the Fourier transform of u of t multiplied by e to the power of j omega c t and e to the power of minus j omega c t. So, this will be, we know that u of t has for the Fourier transform 1 over j omega plus pi delta omega. Now, we have u of t multiplied by e to the power of j omega c t, which means instead of omega we have omega minus omega c and delta omega minus omega c. It is also multiplied by half. So, we take that into account. Similarly, u of t is multiplied by e to the power of minus j omega c t. What it means is the Fourier transform of e to the power of minus j omega c t times u of t would be 1 over j omega plus omega c plus pi times delta omega plus omega c. So, on this basis cos omega c t u of t will have the Fourier transform 1 half of pi delta omega plus omega c plus pi delta omega minus omega c because of the multiplication by this. In addition, you have 1 over j omega minus omega c plus 1 over j omega plus omega c. You put all these terms together, you can show that this will be equal to pi upon 2 delta omega minus omega c plus delta omega plus omega c, two delta functions, plus j omega by omega c squared minus omega squared. So, the spectrum would be like this. At omega c and minus omega c, you have delta functions. Of stance pi upon 2. In addition, you have a continuous variation of the magnitude corresponding to omega over omega c squared minus omega squared. So, something like this it will be. You observe that we are not taking a pure cosine wave lasting from minus infinity to plus infinity. If it had been a cosine wave lasting from minus infinity to plus infinity, there is only one single frequency term that is present, therefore, you would have spikes at plus omega c and minus omega c. This is not a pure cosine wave, it is cut off for negative values of t, therefore, it is not a periodic phenomenon lasting from minus infinity to plus infinity. Therefore, you have other frequency components, not only the infinite the coefficient density at plus omega c and minus omega c, plus the a continuous band of frequencies with various magnitudes as shown in this. In fact, you can show that if I have a cosine omega c t u t, you can think of this as the sum of a cosine function which lasts forever, this is half cos omega c t, plus the same function repeating for positive half, and but the negative of this occurring for the negative t. So, this is cos omega c t divided by 2 multiplied by signum function of t. So, it is this part which contributes to the delta functions. It is this part which contributes to this term. So, the delta part will correspond to this, and this continuous frequency is. So, that is how it goes. So, a pure cos omega c t u t, if it is a cos omega c t as such without multiplication by u t, it would have been pure impulses at these two frequencies, but because it is not periodic function in that sense, lasting from minus infinity to plus infinity, you have an additional portion of the spectrum like this. Similarly, you can derive the spectrum for sin omega c t u t, but we will not do that in this. I will leave that as an exercise for you. We will discuss one additional property in this lecture, which relates to the convolution. You recall that the convolution of f of t, two time functions f of t and g of t, have been defined to be f of t minus x g of x dx from minus infinity to infinity. So, this is a function of time, and this is defined in this manner, f of t minus x g of x dx. The physical meaning of convolution, etc., we have discussed earlier. Let us try to find out the Fourier transform of this in terms of the Fourier transforms of f of t and g of t. So, the Fourier transform of f t g t convolved with g t can be written as minus infinity to plus infinity of e to the power of minus j omega t times this is the function of time now, minus infinity to plus infinity of f of t minus x g of x dx. This is the function of time, the new function of time dt. This is what the Fourier transform of this would be. This is integration with respect to time t, this is with integration with respect to x. Now, let us interchange the limits of integration. This is t from minus infinity to plus infinity, this is x from minus infinity to plus infinity. Let me interchange the limits of integration. Let us interchange the order of integration. I would like to do integration first with respect to t and then later with respect to x. So, all terms which are independent of t can be put outside. Therefore, I put gx dx, and those which are dependent on t I will put inside the first integral, which is to be done f of t minus x e to the power of minus j omega t. Now, from the property of translation in the time domain, if f of t has a Fourier transform of f of j omega, when you have f of t minus x, the Fourier transform of this we know is f of j omega multiplied by e to the power of j omega x. So, this turns out to be x from minus infinity to plus infinity of gx dx e to the power of f of j omega multiplied by e to the power of minus j omega x. And in this we are integrating with reference to x. Therefore, I can write this as f of j omega can be pulled outside the integration sign, and then you have minus infinity to plus infinity of g of x e to the power of minus j omega x dx, which is the standard formula for the Fourier transform of g of t. Instead of t I have put x, is a dummy index. Therefore, this is indeed g of j omega. Therefore, f of j omega multiplied by g of j omega is the Fourier transform of this. So, that is a nice result in the sense that you have The convolution in time domain corresponds to multiplication in the transform domain. So, f of t convolved with g of t, which is a complicated integral operation, is carries over in the frequency domain or the transform domain as pure multiplication of the two time functions. So, convolution in the time domain corresponds to multiplication in the transform domain. This has very interesting applications in system and network theory, which we will come across as we go along. And in the convolution formula here, when you apply this to Fourier transform theory, all functions of time are assumed to be lasting from minus infinity to plus infinity. So, the limits must be taken from minus infinity to plus infinity. This may be different when we go to Laplace transform later on, but as far the Fourier transform theory is concerned, the convolution you must take from minus infinity to plus infinity. And two time functions which are convolved in time, as far the transform domain is concerned, it is equivalent to multiplication in the transform domain. In this lecture, we first of all looked at the Fourier transforms of periodic functions of time. To start with, a pure DC will have in the Fourier transform a spike, that is an impulse at the origin, and Fourier transform is 0 everywhere else, indicating that the concentration of energy is only at one frequency, that is at DC. Then we took up a sinusoidal function of time, angular frequency omega naught, and we found in the Fourier spectrum we have two delta functions at plus omega c and minus omega c, and therefore, the spectrum consists of two impulses sitting at these frequencies plus omega c and minus omega c. That means, there is no energy at all other frequencies. We extended this concept to a periodic function of time, which admits a Fourier series representation. In the Fourier series, the spectrum consists of lines having a finite amplitude, that is the various coefficients, Cn coefficients, and this is a line spectrum in the case of a Fourier series. But in the case of a Fourier integral, it continues to be a line spectrum because the energy is only at discrete frequencies. But now, since we are talking in terms of coefficient density, the line spectrum consists of a series of impulses sitting at these various discrete frequencies, and each impulse is strength of each impulse is related to the Fourier coefficient in the Fourier series representation by a factor 2 pi. That means, instead of C naught in the Fourier coefficient, we have 2 pi times C naught being the strength of the impulse in the Fourier spectrum. After having dealt with the periodic functions of time, we looked at functions of time like the unit step function or a sinusoidal function which lasts only for positive t, and then try to look at the Fourier spectra of these. We notice that this is not a pure periodic phenomena, this has an aperiodicity attached to it. Therefore, you have in the spectrum concentration of energy at one or more discrete frequencies corresponding to the basic character of the time function. If it is a unit step function, the concentration of energy is at DC. If it is a cosine omega c t ut, then the concentration of energy is plus omega c and minus omega c. But since these are not periodic functions, they are cut off for negative values of time. You have also a portion of the spectrum which is continuous and which is representative of an aperiodic function. Therefore, you have a continuous spectrum as well as one or more lines representing the particular frequencies which are present. We saw that in the analysis of such functions, the signum function plays an important role. Signum function is one which has got -1 for negative t and +1 for positive t, and we saw a signum function as the Fourier transform 2 upon j omega. Lastly, we looked at the convolution property in the time domain and how it is goes over in the transform domain. Two time functions f of t and g of t, when they are convolved in time domain, in the transform domain, the resulting function of time will be having a Fourier transform which is the product of the Fourier transforms of the individual components which are convolved together. In particular, f t star g t, which is the convolution of f t and g t, has a Fourier transform which is f j omega times g f j omega. This particular property is very useful in network and system studies, as we will see later. And in the next lecture, we will start off with an example illustrating the convolution property, and we will go on from there.